This video is going to be all about inscribed angles. Now, up till now, all we've talked about regarding angles and circles are central angles. And remember, central angles had a vertex at the middle, right, the center of your circle. Now, these inscribed angles are different. They're going to have their vertex on the circumference of the circle, and they're created by two intersecting chords or secants. So let's go ahead and jot down that definition. So once again, an angle with its vertex on the circumference of the circle, which is different from that central angle because we're going all the way to the circumference of the circle, pulling it back, and then created by two intersecting chords or secants. So let's go ahead and draw an example. So you basically just have two chords, something like this, right? And they'd meet on the circumference of your circle. So we can call this A, B, C. So this angle ABC is an inscribed angle. And we're going to have a few theorems we're going to talk about regarding how to figure out stuff with these inscribed angles. But it's going to boil down to the first theorem, the inscribed angle theorem. Before we get there, there's a couple more vocabulary words that you're going to want to be familiar with here. So we can have our inscribed angle create an arc, and that arc is called the intercepted arc. So we're going to be looking at this arc that kind of is the mouth of your angle. So if you look from A to C, this arc is created by that inscribed angle. That is the arc that we call the intercepted arc. So AC is the intercepted arc. All right. And then finally, we can also have a chord subtend our inscribed angle. And basically that just means the chord that's created by the two endpoints of the legs of your angle. So if you connect A to C, and you see how this is the chord connected to that arc, that's the chord that subtends the angle. So we'll say the chord AC subtends angle ABC. And you might see that in some directions, or you might hear it described that way, so you just want to make sure if you need to draw it out, you know what that means. Okay? So our first theorem, the inscribed angle theorem, which is basically the foundation of all the other theorems we're going to be talking about today, basically says that the measure of your inscribed angle is 1/2 the measure of its intercepted arc. Okay, so you want to make sure you're jotting that down. So you see how this is different from the central angle. The central angle goes to the middle, so it's the same measurement as your arc, but now we're pulling it all the way to the circumference, so now it's 1/2. So if we keep using that picture, we can say the measure of angle ABC is 1/2 the measure of arc AC, that intercepted arc. Okay? Now, a corollary that relates to this says that if inscribed angles intercept the same arc, then they are congruent. And that again just makes sense because we'd have the exact same arc. So let's scroll down and jot that down. Again, if inscribed angles intercept the same arc, then they are congruent. So what would this look like? For example, if you had a circle, and let's say we had one inscribed angle ABC and a second inscribed angle ADC, you'll notice how they share the same intercepted arc, that same AC. That means they'd be congruent. So we'd say angle ABC is congruent to angle ADC. Okay? So that's a corollary that just kind of relates to that inscribed angles theorem. But let's go ahead and use that theorem to talk about example 1. So I want to go ahead and find the measure of x, and you know what I realized? I totally forgot to give you the other value. So this value hi is 4x minus 6 degrees. So let's pretend that I wrote that down already. All right. So if we have HGI is x plus 5 and HI, that arc, is 4x minus 6, what's that relationship? Well, hopefully you remembered that the measure of your angle, HGI, is equal to 1/2 the measure of the arc, HI, by your inscribed angle theorem, right? Again, if it was at the center, then they'd be congruent, but because we're all the way out to the circumference, it's going to be 1/2. So let's go ahead and substitute to solve. So x plus 5 is equal to 1/2 of 4x minus 6. Now again, just be careful with your algebra. Make sure you distribute that 1/2. So we'll get x plus 5 is equal to 4x. Or sorry, see, I didn't even distribute there. Easy mistakes to make, so be careful with that. So we want to make that a 2x minus 3. And then we can solve, right? So I can subtract x from both sides, add 3 to both sides, and x will equal 8. All right. Let's go ahead and move on to the next theorem, which relates to, again, inscribed angles, but one inscribed angle in particular. So we're going to look at what happens when we go through a diameter. And you may actually be able to think about this. So let's say we have a center A here, and we create an inscribed angle that happens to have endpoints on the diameter. So let's call that x, y, z. Take a moment and I want you to think what the measure of that angle y would be based on the idea that xz is a diameter. Well, hopefully you guessed that since your diameter cuts your circle in half, and that's 180, we divide 180 by 2 to get a right angle. So you notice this is a biconditional because it has an if and only if, which means it goes both ways. So we can say if xz is a diameter, then the measure of angle xyz is 90. Or we could actually just say angle xyz is a right angle. Let's go that way. But remember, since it's a biconditional, it goes both ways. So we could also be told that, hey, if angle xyz is a right angle, then xz is a diameter, right? Because that's what makes a semicircle. So that one's a pretty clear one. Just make sure you check for that dot in the center. We need to make sure that's a diameter.